Hello, class. Lecture 7, LiDAR perception. So this lecture, we're going to introduce you to LiDAR-based perception techniques. Before we talk about 3D object detection, we're going to give you a quick introduction to principles of LiDAR, how LiDAR works, and what types of LiDARs are out there. And then we'll dive into 3D object detection algorithms, where problem definition evaluation metric is used, and how traditionally this problem has been tackled, and how recent learning methods approach about 3D object detection using LiDAR point clouds. Here's the working principles. I think I briefly explained this, when in the introduction to perception. Let me introduce this one more time in more details. So it basically works like a pointer that we use for presentations, but we rotate. So using this type of mirror, we rotate in space so that we change the direction of the ray, the laser ray, and then we measure the distance by calculating time of flight. Then we can find the distance. And because this is a laser pointing, laser-based measure, what we get is a point, a very accurate and very small point value. So what you get out of the LiDAR is a series of point values, and when you have a single laser pointer, then you get this two-dimensional information about the space. But when you have multiple lasers shooting into the space, let's say vertically, and rotate horizontal direction, then you get 3D information. And we call that point cloud, okay? The point clouds look something like this. It's a collection of LiDAR measurements expressed as X, Y, Z, and I, where X, Y, Z are 3D coordinates, and I is the intensity. One characteristic the LiDAR output has is it's unordered and irregular set of points that describe an object or surface. So when you visualize, then you get this nice sort of surface or object contour, where human are used to. But when you actually look at the raw data, then they are unordered. So when it comes to later on, we'll talk about this later on, but when it comes to signal processing, sometimes it's more difficult to handle because there's no order when it comes to processing these signals. We'll talk more about that later, but that's one of the nature characteristic of LiDAR point clouds. And there are different types of LiDAR. Most widely used and popular LiDAR is the scanning LiDAR. So there is a mechanical rotation to spin the sensor for 360-degree detection. So the nice feature of this scanning type LiDAR is that you get a full 360 field of view using one LiDAR. So that's a nice feature. But then of course, there are other limitations. It required, such as it requires this mechanical rotation device, such as motor, and it needs to physically rotate laser and receiver assembly. Or you can do it by rotating a mirror. And if you need multiple channels, you need multiple laser emitters in vertical axis. Usually, this LiDAR tends to be high cost and prone to durability issues. Well, both the cost and durability maintenance issue is coming from this, the laser, the nature of the laser. So in order for you to emit a laser point and then receive that signal and be able to tell and compute this distance, you really need high precision devices, and a lot of calibration is necessary. So in the old days, this had to be done by human engineer or manufacturing personnel had to do a lot of tuning and calibration, which leads to human labor. So that leads to higher cost, and then also if things vehicles actually undergo a lot of harsh environment and very hot, very cold weathers. You may have to go through off-road, and under these harsh conditions, LiDAR can be quite sensitive sensor to use because of this highly accurate sensor nature, which required calibration. So if something gets misaligned, then your sensor output can easily give wrong information. So these were one of the critical issues for vehicle to use LiDAR, but there are new more robust LiDAR sensors used for automotive applications. So to mitigate these problems, there are other LiDARs currently developing, and people call them usually solid state LiDAR. And there are multiple types. There's MEMS LiDAR, where these mirror is designed using MEMS device, very small actuator and mirror moves the direction of the laser so it can scan the environment. So that the device can be smaller, smaller and less, more robust to, those harsh environments, hopefully, and noise, vibration, harshness, those can be less of a problem. And then there's better methods, such as OPA, optical phased array lidar. And then there's flash lidar. So MEMS lidar is not, technically, I think speaking, MEMS lidar is not perfectly solid state lidar. I consider that scanning lidar, but using MEMS device. But these OPA and flash lidar are true solid state lidar. So OPA basically scan or steer the laser lights by using optical phased array. And then there's a flash lidar that emits laser lights just like a flash, towards one direction, and such as this drawing. So you send out a laser, and then you have sensor that measures reflected laser lights, and then you do signal processing to compute distances throughout the whole space, the forward-facing scene. But they seem to be very good, promising high tech. But one company developing OPA didn't quite deliver the product. They always claim that they will be able to develop OPA lidar, in the next 2-3 years, with low cost mass production, like $200-$300 cost. But that was like 8-9 years ago, and it turns out they failed. Flash lidar also seems very promising, but similar to OPA lidar companies, there is working models, but they tend to have very low resolution, and then the range tends to be very short. So object that is only close to the lidar can be accurately detected, but the maximum range of the light coming back tends to be short. So not very suitable for automotive applications. So OPA flash lidar is really, really nice, promising technology, but it's difficult to develop. MEMS lidar seems to be coming into the market, and they are more practical technologies, but it still has that moving part. Although it's light, small, and compact, it still has that scanning device in it. Okay. All right, let's move to 3D object detection. traditional approach goes as follows. The pipeline goes composed of three parts: data preprocessing, and then ground removal, and then clustering. The preprocessing, select and view only necessary data, and we go through ground removal so that we focus on detecting objects, and then the clustering, cluster points and detect objects. Okay. Preprocessing. Point cloud data received by LiDAR can be cut by setting the top and bottom heights or by setting the horizontal range. So usually the LiDAR has this vertical field of view, which is which is defined by the vertical angle field of view. So when the range, when your detection range, extends to the distant, then you can have point clouds that's actually in the sky or ground. So here's the ground points, right? So but when driving, we are probably interested in objects that are in this region. So what this description is saying is we can remove these points, and then another processing would be downsampling. So depending on the LiDAR gives you many point cloud points in the data. But when it comes to processing, using all point cloud data will require a lot of computations. So usually downsampling is done so that for a given space, there's one or two points in that space, a voxel, sometimes called a voxel. So you downsample, you basically drop so when you have 5 points in one cube or voxel, you downsample, meaning that you pick only one of them and remove other points. Okay. And then there's ground extraction. So when you have LiDAR point cloud, you have this circular shaped point clouds, but usually that corresponds to the ground, which we are not interested when it comes to object detection. So we can remove those point clouds. Okay. And then clustering is the key to object detection. And there are different clustering methods, but the most widely used method is clustering based on Euclidean distance. So when we have point clusters, then we can consider that as one object. So we can cluster them, we can cluster points, and then we can detect objects based on clustering methods, and then classify points with close Euclidean distance into one point cluster and detect objects based on the cluster. Okay. And the final stage is going to be the detection in order to perform 3D object detection on cluster data, 3D bounding. 3D bounding box is often used to detect vehicles. Of course, other types of shapes can be used for different objects, and usually classification algorithm is also applied to classify whether they are a vehicle, pedestrian, cyclist, and so forth. So when to give you an idea, this traditional LiDAR-based detection algorithms are still widely used for many autonomous drivings, because when we use deep learning and when we use camera image, we require high computing power, and as well as even if we have good high computing power hardware and software, camera-based approaches can fail. So when it comes to reliable product, selecting reliable product, robust product for autonomous driving in real world, people tend to go with LiDAR-based perception, because LiDAR is accurate, reliable, robust, generally speaking, relatively, relative to camera or radar. So many of the level 5 or level 4 autonomous vehicles almost always use LiDAR sensors, and many of them actually still use traditional approaches, and sometimes they do use deep learning based approaches if they want to really push the limit and maximize the perception performance. All right, let's move to 3D object detection using LiDAR, and let's talk about learning approach. Hello, class. Let's continue with 3D object detection learning approach. Learning-based 3D object detectors have evolved over the last 7 or 8 years, and there are number of object detectors available in the literature, and I would like to give you a quick overview of what types of LiDAR object detectors are available. Here's a taxonomy of the networks. So first, let's group by the backbones or encoding methods. Let's first start with voxel. I will give you a more detailed introduction to these types of encoders in the following slides, but the encoder can be divided into 2 types, voxel and point. And there's a few methods that utilize both point and voxel encoders. And then there's we can also classify detectors networks into two types, one being one stage and the other being two-stage detectors. As you can see, there are more voxel-based networks out there. And we'll talk about both approaches, voxel and points. Here's a comparison or key feature or function for each type of network, where encoding type and number of stage is listed. And let's go by one in the following lecture materials. But you can come back and take a look at these lists and features to review the materials. Okay. Here's another good figure for you to for you to have a good overview of different types of LiDAR object detector. Here, this figure is taken from. There's no citation here, but anyway, this paper and the site is maintained by these authors, and if you look up the literature, you will be able to find this figure and the manuscripts explaining different types of object detectors. And this is a good overview because they tried to come up with one sort of unified or universal architecture and try to highlight which network uses which module within this generalized unified architecture. So for instance, here's the VoxelNet second architecture, and the general unified architecture includes both 3D backbone, 2D backbone, and then ROI head and dense head. So what this indicates is that there are 4 modules, but depending on the network, some networks have 3D and 2D backbone and dense head, but VoxelNet second does not have this ROI head, which is sort of proposal network. So this indicates that this one is a single stage network. And if you take a look at part A2 net, this network uses this ROI head pipeline module. So that indicates that this is 2-stage network. Okay. And then we can also see that let's take a look at this network, VoteNet 3D SSD. This one uses PointNet encoder, which I will explain further later, and then directly goes to dense head, which regresses the 3D object detection metrics. So by having these, generalized, unified general architecture and indicates which module is activated, which module is not inactivated, we can see that how each detector is composed of different modules. Okay, so this is a good overview figure. So let's talk about, first of all, let's talk about encoding network, backbone. So there are two types of encoder when it comes to LiDAR point cloud encoder. One being point net, which uses point cloud directly as an input, whereas we have voxel-based encoder, which uses this voxel structure and downsamples points depending on the density of point cloud within the voxels. So let's take a look at the point net first. So point cloud characteristics are listed here. The point cloud is unordered, invariant under transformations. It's meaning that when you rotate, translate, the point cloud does not change its shape. Okay. And interaction among points, there are also invariant, but one of the downside of voxel is that large amount of computation in 3D convolution if you want to use voxel-based encoder. So this was sort of motivation for point net. By the way, please take a look at this reference citation. This is only 2017. So this backbone was proposed in 2017. Before then, people were not really, working towards the point cloud-based, detection problem or segmentation problems. People were focusing more on the vision or image-based problems. So, and this was one of the early work that proposed point cloud, backbone for point cloud. So people started to use this, point net afterwards. Okay. Let's go over these bullet points. Point net is architecture for extracting semantic features from unordered point sets. It should be permutation invariant, which is resolved by max pooling function. Use a spatial transformer network that attempts to canonicalize the data before the point net processes them. So the problem is we have a set of 3D points and we want to do classification and segmentation for this point cloud input. Here's some of the key features. So symmetric function for handling order permutation, meaning that f of x would be somewhat similar to G of H of X, where H being multi-layer perceptron and G being max pooling function. So if you look at this architecture, you have classification network, and then you have segmentation network, and then you get and for each layer you have these TNet network that allows do these type of requirements or functions for PointNet point-based encoding. And point segmentation, for point segmentation, it uses concatenate the global feature with each of the point features and extract new per point features based on the combined point features. So it takes this point features, and then after you go through this layer, you take the global feature, and then you concat both features, and then you create another layer for the header, the segmentation network. And this layer is to classify a task. And it has this joint alignment network that attempts to do these tasks, align all input set to a canonical space before feature extraction, predict an affine transformation matrix by a mini network called TNet, and directly apply this transformation to the coordinates of input points, constrain the feature transformation matrix to be close to the orthogonal matrix. So that would be the loss for the alignment. And this was, like I said, very early point-based encoding network, and the segmentation was one of the tasks they focused on for as an application. And here's the results. They did some ablation study, and they played with different pooling and different networks, and they were able to obtain decent results. Again, this at this point of time, there were no good point backbone for point clouds. So this was very early work. And then this PointNet evolved further. And you can see this work is 2017, published in NeurIPS 2017, and they called it PointNet++. So the motivation was original PointNet does not capture local structure induced by the metric, and hierarchical neural network that applies PointNet recursively on a nested partitioning of the input point set. How to generate overlapping partitioning of a point set. Centroids are selected among input point set by a farthest point sampling algorithm. What this means is that this original first generation point net did not have this hierarchical feature abstraction, where many of the image CNN backbones does have hierarchical feature abstraction characteristics. So they try to apply similar function and feature into this backbone network by introducing the hierarchical feature abstraction layers. So here's the figure that explains that concept. So set abstraction level. At each level, a set of points is processed and abstracted to produce a new set with fewer elements. Sampling layer selects a set of points from input points, which defines a centroid of local regions. Grouping layer then constructs local regions sets by finding neighboring points around the centroids. Point net layer uses a mini point net to encode local region patterns into feature vectors. So what does that mean? Here's more descriptions. So density adaptive point net layer handle non-uniform density of point cloud, meaning that in some space there's more points, whereas in other area there's sometimes there's no point at all. So it needs to be handle these non-uniform density of point cloud. And then there are two technique is employed, multi-scale grouping and multi-resolution grouping. Multi-scale grouping means that when you extract feature, you are going to look at different region, different size of the region, and then extract features within that space. So that is multi-scale grouping. And then for multi-resolution grouping is that in one layer, you are going to extract features from this space, and then this space, and then this space. And then one layer above that, you are going to extract features from the entire space, but using this extracted features. And then you have another feature extraction vector that extracts entire region, but from the low level features. So here this has hierarchy, okay? So, and that is what is introduced in this section, okay? So the input is point cloud, and then you have small, you have these type of small mini network for feature extraction. But then you also have this hierarchy, and then set abstraction to be able to have hierarchical feature abstraction extraction functionality, so that you can you can have features for both low-level feature as well as high-level features for point cloud inputs. Again, here is two header, two segmentation, and trains using two tasks. So that was point net, point cloud direct point based encoder. Here is another encoder, which is voxel encoding network. This network is much more intuitive and easier to visualize, because the idea of voxel encoding is we are going to make a three-dimensional grid within the three-dimensional space. So we have these boxes has dimension of d by h by w. So basically, within the perception space, the space we are interested in, we're going to create these grid where each different size of I'm sorry, let me take that back. So these multi layer box grid is stacked up to in these vertical direction. So I'm not sure if that is easy to visualize. So we have these grid in two-dimensional space, and then we have another axis for the vertical height direction. So that creates boxes basically, and that's called voxelized space. And then what happens in the voxel encoder is that you create this within the grid space, you group things into each voxel. So you have different number of points for each voxel, and then you do sampling, random sampling, which is to downsample the number of points within the voxel, so that reduces number of point cloud, so that also helps reduce computational load. And then you create feature out of those voxel, and then you go through stacked voxel feature encoding. So this is the key part, and it goes through this layer called stacked VFE layers, which sort of like 3D CNN. 3D convolution further aggregates local voxel features, transforming the point cloud into a high-dimensional volumetric representation. RPN region proposal network consumes the volumetric representation and yields the detection results. Voxel partition and grouping. So I already explained this concept, both bullet points. Okay, so let me give you a little more description on this part. Stacked voxel feature encoding, VFE. So you compute the local mean as a centroid of all the points in voxel. Augment each point pi with the relative offset with respect to the centroid, such as this form. Find the voxel descriptor using PointNet and concatenate it to each point-wise feature. So you're adding this offset value, augment that with offset values for each point. And you apply sparse 3D convolution because this is 3D-dimensional space. You have 4D tensor, where C is the dimension of voxel-wise features. But if you look into this tensor, 90% of the voxels are empty because we're dealing with 3D space, and if you let me take a look at this type of example. You have these point clouds, but then other space has no point clouds. Okay, and another example can be shown here. So there will be number of points if there's an object, but in the rest of the space there's no points. So there are many voxels without any point within them. So why do we compute? Why do we compute the feature vector abstraction or extraction for these empty spaces? That's not very efficient. So what people proposed was sparse 3D convolution. So what it means is we are not going to compute feature extractor for those empty spaces. Okay. Region proposal network, apply additional convolution layer, produce the classification scores and the 3D box regression results. So this is the sparse convolution layer. So this network is called second. Sparsely embedded convolutional detection. So voxel, the early voxel-based network was VoxelNet, which tends to run slow. So second proposed this sparse convolutional method described here. So you take voxels with point features, and then you run the convolution, and then you reconstruct the output feature vector or tensor in this manner. So this substantially increased speed of voxel-based object detector. And then also introduced additional laws for the angle orientation regression. And this shows how much second improved the speed from 0.225 to 0.05 second. Okay, and the performance also improved significantly. And then the next network is point pillars. This one was proposed in 2019, so it's not too long ago. And what the key idea of point pillar is that why do we perform 3D CNN? You know, when we have you know, very efficient and effective 2D CNN networks, right? So what they proposed was they're going to make the voxel into 3D space into 2D image, 2D grid, by aggregating the vertical Z direction voxels. So that's why it's called a pillar. So rather than having these voxels, if they aggregate Z direction, they're going to have this pillar. Okay, so what this also means is that if you look at, we can also look at this from top view, bird's eye view, and then it'll just simply look like a grid, 2D grid. Okay, so by making the feature space onto this 2D grid, we can apply 2D CNN backbones, okay, which is widely used in image-based detector, right? And that's what was proposed. And then if you look at the computational time, that substantially reduced speed further from 0.05 to 0.016. But sometimes in terms of performance, sometimes they improved, sometimes not. So one of the key contribution of this work was to make fast LiDAR object detector. So there was you know, pretty good balance between the performance and the speed. So here's the summary of performance and the speed comparing different networks. It compares VoxelNet, second, and point pillars, as well as other point-based networks. So initially, when VoxelNet was proposed, it was very slow when compared to PointNet. But then after this, you know, faster backbone and networks, you know, voxel-based network improved its speed significantly when compared to PointNet. And if you look at the performance, voxel-based approaches and point-based approaches are comparable. So for instance, we can compare second or point pillar with you know, some of the you know, high performance point-based approaches. Point-based approaches. So after applying, you know, some techniques to improve speed for voxel approaches, it turns out that point-based approaches tend to be slow because here you're using more points. You have to process more points, and then if you're using two-stage, then that adds another computational load. Okay. So people also wanted to improve the performance of point-based object detector, and this is one of more recent works, 2020 CVPR. It's called SASSD, structure-aware single-stage 3D object detection. Excuse me. The idea for of this network was to have this auxiliary network, and so that we can train the network using point level supervision. But when you're actually running this in real time for inference, you don't have to use this auxiliary network that were used for training purposes. Instead, you can do only these two networks. And this auxiliary network, provides some of these, features based on the hierarchical feature abstraction ideas that we discussed earlier. So there are many approaches, networks out there. I'm not going to describe every network during lecture, but as you can see, the point cloud based object detector also evolved over the last 7-8 years or so, and their performance has been improving over time, as well as their inference speed has substantially improved, because usually these applications are robots and autonomous vehicles. So people do care about their running time, inference time. This one is another point-based object detector, 3D SSD. These are the contributions, and continues to improve the performance. Please take a look at these slides in more detail. I will move fast here, and we'll talk more about these during the discussion session. Okay. This one is this one, let me quickly point this one out. This one is interesting because it uses both point and voxel feature for 3D object detection, and it does give you some performance improvement, but the computational load and the complexity of the network significantly increases. So if you go back to the taxonomy, people did not quite investigate it further into these hybrid type networks. Oh, these slides give you a good summary of comparing different networks. So here's one stage, two-stage networks, and comparing their speed as well as performance. As you can see, the voxel-based approaches are somewhat faster than the point-based approaches. And performance initially, point-based detector was performing better initially, but then later on, recent voxel-based networks are comparable to point-based approaches. Here's more details about their performance, depending on the types of data, test data. This one is car detection, pedestrian detection, cyclist detection, and you can see which network performs better than the others. Okay. So this is it for today. So please submit your questions by tomorrow, and we'll discuss that during the discussion session. Okay. Thanks for your attention, and see you on Wednesday. Bye-bye.